So here's a chart that shows the historic temperatures of carbon dioxide concentrations. If you carefully look at that blue line, we can see that temperatures have changed dramatically over the past 400,000 years. Most of these rapid shifts have occurred during an onset of an ice age or during the transition from an ice age to a period of warmer temperatures after an ice age. But because these changes occurred before humans really could have affected the global system at all, scientists suspect that the changes were caused by small, regular, normal shifts in the Earth's orbit. The path of the orbit and the amount of Earth's tilt on its axis and the position relative to the actual sun all change regularly over hundreds of thousands of years. So these changes, they alter the amount of sunlight that actually hits the northern latitudes in the winter and the amount of snow that can actually accumulate because of that, and the way that the albedo keeps energy from being absorbed and then converted to heat. So all of these things, these changes could give rise to fairly regular shifts in temperature over longer periods of time. But the more important insight from this diagram is the close correspondence between historic temperatures of carbon dioxide concentrations. This graph does not tell us the nature of the relationship. Did periods of increased carbon dioxide cause increased temperatures? Was that because of an increase in temperature due to the production of CO2? Was there another factor at work here? Scientists believe that the relationship between fluctuating levels of carbon dioxide and the role, how it's related to temperature, they're very complex. And so all of these things play a role. We know the increase of carbon dioxide in the atmosphere causes a greater capacity of warming throughout the greenhouse effect. However, when the Earth experiences high temperatures, the oceans warm and they cannot contain as much CO2 gas. They can't hold on to it as well. And as a result, they release it into the atmosphere. When ultimately this matters because the net movement of carbon dioxide between the atmosphere and the ocean is basically how the feedback loop works together in affecting global temperatures. We can also examine temperatures over shorter periods of time. Scientists have used indirect and direct measures to determine global temperatures during around the past 2,000 years. They then selected an average temperature between 1900 and 2000 as basically like a baseline at which all other years can be compared. They use this baseline, which isn't shown in the presentation, as almost like zero temperature change. So once they set a baseline, then they can show the fluctuations over 2,000 years and kind of compare it to temperature change that has happened over a longer period of time. All right, so just as indirect indicators can help us get the picture of what temperature has been in the distant past, computer models, they can also help us predict future climate conditions. So researchers have determined how well a model approximates these real-world processes by applying it to a time in the past for which we have accurate data for. And we have some good data on conditions like air and ocean temperatures, carbon dioxide concentrations, the extent of all the vegetation that was on the planet, and sea ice cover, and that was over the poles. So these modern models, they reduce recent temperature fluctuations well over large spatial scales. And from this work, modelers or scientific modelers, they're fairly confident that the climate models capture the most significant features of today's climate. And although climate models cannot forecast future climates to complete accuracy, as the models improve, scientists have been able to place more confidence in their predictions, especially when it comes to temperature change. Although they have had more difficulty predicting change in precipitation, on the other hand. But because assumptions vary among different climate models and when multiple models predict similar changes, we have seen an increase in the confidence that has come out of this particular scientific community. The global greenhouse system is made up of several interconnected subsystems with many potential positive and negative feedbacks. We've talked about this before in that populations unit Positive feedbacks, they amplify change. So because of this, positive feedbacks often lead to an unstable situation in which small fluctuations of inputs lead to a large observed effect. On the other hand, negative feedbacks dampen change. When we think about how anthropogenic greenhouse gases will affect Earth, we must ask whether positive or negative feedbacks will predominate. We do not currently have enough evidence to settle this question conclusively anyway, but we can examine some of the feedback cycles and the way they influence temperatures on Earth. All right, so positive feedbacks, there are many ways that they raise temperatures, and that could create a positive feedback. For example, global soils, they contain more than twice as much carbon as the amount currently in the atmosphere. So shown in this figure here, high temperatures are expected to increase the biological activity of decomposers and inside of these soils. And because the decomposers, they lead to they release additional carbon dioxide from the soil into the atmosphere, the temperature change will be amplified even more. And that's a positive feedback. A similar but quite more troubling scenario is expected in the tundra biomes, where the tundra contains permafrost, if you remember. So atmospheric concentrations from human activity sources, they've increased, and the Arctic regions become substantially warmer than others, and the frozen tundra begins to thaw. As it thaws, the tundra develops areas of standing water with little oxygen available underwater as it is. These organic layers of the tundra also start to decompose, and as a result, material experiences this anaerobic decomposition, and that actually produces methane, which is a far more stronger greenhouse gas than carbon dioxide, which should lead to even more global warming. All right, on to the negative feedback. One of the most important negative feedbacks that occurs is plants respond to the increased atmospheric carbon. Because carbon dioxide is required for photosynthesis, an increase in CO2 can stimulate plant growth. And this growth of more plants will cause more carbon dioxide to be removed from the atmosphere. This negative feedback, which causes carbon dioxide and temperatures to increase, but at a much smaller scale, would otherwise appear to be normal or about half of the normal CO2 emitted. So, and this is into the atmosphere, by human activity, and it still remains there. A second negative feedback exists in the oceans. As carbon dioxide concentrations increase in the atmosphere, more carbon dioxide is absorbed by the oceans. And although this is beneficial and it reduces the CO2 in the atmosphere, it causes harmful effects on the ocean. When carbon dioxide dissolves in water, much of it combines with the water molecule to form carbonic acid, which is H2CO3. And since at equilibrium, these reactions inside the ocean cause CO2 to be converted into carbonic acid, when that happens, this will lower the overall pH of the ocean. This process is called ocean acidification. And ocean acidification is a particular concern because there's just a variety of species that live in the ocean, and they build shells, and their skeletons, they're made of calcium carbonate, things like corals, mollusks, and small crustaceans. So as the pH of the ocean decreases, the calcium carbonate in these organisms begins to dissolve, and the ocean saturation point of calcium carbonate pretty much declines, which it's much harder for the organisms who live there to acquire the material that they need in order to build their shells and their skeletons. Most of the feedbacks we've discussed are limited by features of systems that take place. The one example of the soil carbon feedback, that's basically limited to the amount of carbon in soil, right? While warming of the soils can add a large amount of carbon dioxide to the atmosphere over time, eventually soil stocks, they will become low in biological activity, and it'll fall back to its earlier normal rate. So in this section, we learned that the concentrations of greenhouse gases have been steadily increasing in the past century. And the production of these gases basically is different among nations in China. And at the same time, global temperatures have also increased since 1880. And we've also seen how scientists, they've estimated temperatures of all the greenhouse gas concentrations for the past 500,000 years. And the species composition of the Earth has actually changed as well. So by examining those small protists and by examining the gas bubbles inside of the frozen water, essentially, together this data set predicts and shows this relationship between carbon dioxide and the overall global temperature change. And we're talking 400,000 years. So we can use climate models to predict the future change in global temperatures under different types of scenarios, whether it's a small, a medium, or a high increase in carbon dioxide. So lastly here, we will examine the consequences of our current future rate.